Okay, so thank you, Stephanie. Very nice of being with everybody for this webinar for my Duncan Art Derry medals. So for those who are not aware, uh, Duncan Air Derry is a prominent member of the GAC history. He's a founding member of the Geological Association of Canada. He was twice its president. He's known as an exploration geologist that worked on a number of commodities, and he was elected as a Fellow of the Royal Society of Canada and an Officer of the Order of Canada. So it's really one of our geologists in Canada that was one of the most distinguished, and this medal is named after him. One of his most important contribution was the World Atlas of Geology and Mineral Deposits, so a forebearer of looking at the overall global distribution of deposits in their geological context. And I'm holding here his book that is still available in the library, so you can look what it was. When he published that in the early 80s, it will give you an idea of the distance we've traveled so far. Before I start, I would like to acknowledge the help of the many people that have brought me to work on orogenic gold deposits first. And for all, François Robert was the one who actually enticed me to work on the Val-d'Or vein field more than 30 years ago. And it's still an ongoing project where we're still learning things and coming with nice new ideas. The work I will present is also the work that has been conducted with a lot of students and colleagues, which have helped me, which I've been privileged to work with and collaborate with. I want to acknowledge the long-term support of NSERC for my fundamental research and partnership research programs. That's been really enabling the research I will present today. And I think we have had two major initiatives in the last 20 years in Canada, the CIMIC Footprints projects and the Metal Earth program that really provided a lot of new information, a lot of funding to carry out projects, and that's really contributed to my understanding of the orogenic gold deposits. And of course, this would not have been possible without the team that we've assembled at Laval with the Agnico Eagle Eldorado Gold Quebec Research Chair in Mineral Exploration, and my colleagues, Carl Guillemette, Christelle Laflamme, Bertrand Ratier, and Renaud Soucy-Laroche, with the support of Agnico Eagle Mines, Eldorado Gold, Ministère des Ressources Naturelles et Forêts du Québec, and of course, NSERC. So let's move to the main subject of the presentation. So let's start with the main characteristics of orogenic gold deposits. What are we talking about? So one of the characteristics of orogenic gold deposits is that they occur along major crustal shear zone. And we can see here the Lauder Lake, Cadillac, and all the dots that line this are gold deposits. And we have the Porcupine, Destor shear zone with the same setting. And another example here is the Lefroy Boulder Fault in the Yilgarn Craton, which illustrates another characteristic of orogenic gold deposits, which is that although there's a major shear zone that's running through the area, the dots showing the deposits are not actually located most of the time on the major crustal break, but they are actually nearby some distance in subsidiary structures. Another characteristic is that they have a quite common setup in terms of structural setting. And this has been nicely summarized here with a deposit that have a fault field vein, which is a shear vein in a shear zone where we have foliation that is developing around it, where the vein is complex. Often it's ribbon because of continuous movement in that shear zones. And there are extensional veins which are orthogonal to that major shear zone, to that shear zone, which record opening in a vertical direction. So this is a common setup for the structural setting of these veins. And when they look in the field, well, we have here a fault field vein that we can see. We can see these ribbons, which are slip planes that record deformation within the fault field veins. And then we have extensional veins that are either contemporaneous, younger, or here older than some of the slip planes, but not all of the slip planes, which indicate multiple deformation event, and that the extension veins are broadly contemporaneous to the shear deformation. So that's a common characteristic to these deposits. If we look at some of the extensional veins, we can see here tourmaline, which is growing from the wall of the rocks, and sometimes they show a curve pattern indicating the curving of the least strain direction during growth, and they are surrounded by relatively narrow alteration envelopes, as shown here. And in the shear veins and the extensional veins, we preserve evidence for open space crystallization of vein minerals. Here we have a fragment of a wall rock, which is within the fault-filled veins. And around that fragment, we can see needles of tourmaline growing from the edge of the fragment of wall rocks with carbonate and pyrite, attesting to the growth of these minerals in open space. And that will be more or less obliterated by successive event of deformation. But it provides us the geological archive from which we can obtain a stabilized isotope composition to calculate important parameters on the origin of these deposits. So I will start with the Val-d'Or vein field because it's one of the classic examples of this deposit type. So the Val-d'Or vein field comprise a large number of quartz carbonate tourmaline veins within broadly this region here. And these quartz carbonate tourmaline veins have similar structural and mineralogical composition. So they are considered to have formed within the same fluid system over time. Now, one of the characteristics of orogenic gold deposits in terms of their stabilized isotope composition is that if we look at the oxygen isotope composition, the minerals, such as quartz, which is the most studied mineral in these deposits, show a low variance in the composition. So here we have the comparison of the delta 18O value of quartz, two types of quartz, one of milky, one is translucent. It's not very important. What is important is all the quartz plot within approximately the analytical error of the method, which means that within our analytical uncertainty, they are basically homogeneous. It doesn't mean there's no change, but there's no measurable change. Here's another example from where we can see a long strike and down dip along a single structure. And although there are variations, they are all within analytical uncertainty. So this is a characteristic where there's a small variation within a deposit that marks that characterize the oxygenized isotope composition. However, when we look at different deposits, and here we have an example from Beaufort, so we see that we have a lot of different analyzers for various types of quartz. They are all similar, and the standard deviation of the 50 measurements in that deposit is again equal to the analytical uncertainty, although the range is much larger. So there are processes happening within the deposit, but the uncertainty is equal to the variance in the deposit. And we can see that in other examples. So this is from the Victoria vein field in Australia, Bendigo, where we can see that each of the deposit has likewise a narrow oxygenized isotope range of compositions, but each of the deposit is slightly different. We can find this characteristic also at the microscale. So this is an example where we have looked at the oxygenized isotope composition in the vein materials with the SIMS. And if we look at the vein materials using a cathodoluminoscope, what you can see is that we have zoned quartz, quartz 1, which is partly obliterated by a younger quartz, quartz 2, which is the product of the ductile deformation that happens during the repeated events of deformation in the veins. But then we also have a later quartz, which we can see here as tiny fractures that cut across here pyrite, and some of these veinlets contain native gold. So we have evidence for dynamic recrystallization of that quartz, brittle deformation of that quartz that produce the today quartz isotope composition. Now, if we compare the various stages of quartz, and I should perhaps come back here and remind that quartz 1 is the original euhedral quartz, that sometimes we preserved. It's partly overprinted by the deformed quartz, quartz 2. And then there are different types of cross-cutting quartz that are slightly different in terms of their cathodoluminescence response. Quartz 3, quartz 4, which makes a veinlets that are brittle, and very rare bright white quartz, quartz 5. So if we look at the oxygen isotope composition of these different types of quartz, what we can see is that there's a general increase from the quartz 1 to quartz 4 or 5. And this general increase is always towards higher values, slightly higher values, up to 3 per mil, but typically within the dynamically recrystallized quartz below 1 per mil in terms of increase in delta 18O values. So the other thing you can see is that each of the 4 localities, the quartz has a slightly different composition, which is like the bulk quartz isotope values that we have from the quartz. The other thing that we did on that study was to look at the trace element of the quartz. And like the stable isotope composition, the trace element in quartz are indistinguishable between the different generations. This all points out to the local remobilization of quartz into the late brittle veins that I showed you before. So we have deposits which have each deposit has its own oxygen isotope composition, but they change from one to the other one. And in the Val-d'Or camp, what we were able to show was that if you look at the regional distribution of the average composition per deposit, what you find is a pattern of regular change from one deposit to the other one. So one thing is that the isopleth, the lines of equal concentration of oxygen 18, cross geological contacts. These isopleths are higher near the Larder Lake Cadillac break, which has a southern margin of the vein field here, and they tend to increase towards the north. But towards the northeast, there's a little change. There's a zone of the high values, indicating another input of fluids that I will discuss a little bit later. So this is the result of 2 processes. One of them is water-rock reaction between the host rocks and the infiltrating fluids. But the second process, which is dominant, is the mixing of 2 fluids that give rise to this regional pattern. And if we look at the higher values and the decreasing values towards the north, then one can surmise that this is the infiltration of the high O18 values close to the Larder Lake Cadillac Fault, and then dispersion mixing towards the north. So this mixing is shown by various lines of evidence. The most important or compelling are the isotope composition of the vein minerals, which show mixing. So what we have here are the composition of water in equilibrium with quartz using the quartz tourmaline equilibrium temperature. And this shows that if you look at the distribution of data, they form an array from a low temperature to an high temperature, low delta 18O fluid to a high delta 18O fluid. So this is evidence for mixing at the scale of the vein field between 2 different fluids. The first fluid, the high temperature, high delta 18O values, must be a metamorphic fluid. It's not the composition of magmatic rocks. And it's most likely that these metamorphic fluids are the product of dewatering at the chloride to amphibole metamorphic transition during prograde metamorphism. Now, this has been a hypothesis that this metamorphic fluid is important for the gold deposit that has been around for some time. Now, what the mixing shows is that the second component is a lower temperature and lower delta 18O value, which I think is an upper crustal fluid. This upper crustal fluid could have been surficial water. In the Archean would have to be seawater, but this water was trapped in the crustal rocks at mid-crustal depth and remained there a long time, so it reached a high degree of water rock equilibrium. So we'll come back to how this happens a little bit later, but the evidence for mixing between 2 fluids is also shown by oxygen and strontium isotopes. So here we have a radiogenic isotope of strontium, which is independent of temperature effects, and the oxygen isotope composition of the water in equilibrium with quartz and tourmaline. And what you can see is that we have a broad array between two end members. The two end members are again the low and high delta 18O values, but we can see that they're also characterized by contrasting strontium isotope composition. So the metamorphic fluid would be characterized by the least radiogenic strontium composition, whereas the upper crustal fluid is characterized by the more radiogenic strontium composition. And that fits with the kind of rocks that would be contributing to this. So we have volcanic and rocks that are least radiogenic in the end member, and we have the Archean carbonate and some plutonic rock high in strontium that are the radiogenic end member. And what you can see is we have two mixing lines with a ratio of 10:1 from the upper crustal to the metamorphic fluid, or 1:20 for the metamorphic to upper crustal fluid reservoir. So we have a wide range of ratios between the two reservoirs that indicate about 200%, 200 times the mixing ratios between the two reservoirs. So that explains why we have this mixing line and that we have two fluid reservoirs that are involved in the formation of these deposits. Another line of evidence for mixing is shown by the hydrogen isotopes, but it provides also additional information. So if we look at the hydrogen isotope composition of the water at the temperature of equilibrium between tourmaline and quartz, what we can see is that we have some sort of a straight array up to a temperature where the variation in delta D values becomes much larger. This happens to be about where we have the critical temperature for the salinity, the typical salinity of orogenic gold deposits. The other aspect of this is that the delta D value of the water are above seawater largely. They go up to almost 30 per mil, and we find that everywhere. So this happens because we have a vector of enrichment of the residual water from the vapor phase separation during boiling or immiscibility. And the repeated events of boiling immiscibility will drive the residual vapor towards high delta D values. If we look at the oxygen and delta D value of water in quartz tourmaline pair in the Val-d'Or field or along the Lauder Lake Cadillac break in that case, what you can see is that there's a large number of water composition that becomes above the seawater composition, indicating two processes: boiling and condensation of the boiled vapor, but also formation of mica and chlorite from the fluid that will enrich the residual water in the heavy oxygen isotope. So if we take this and now look at what's happening when we look at in a fairly simple setting, and one of the case we've studied is the Ogmito-Bouzan sector of the Larder Lake Cadillac break. In this area, which is shown here just south of Rouyn-Noranda, we have volcanic rocks of the Blake River group in contact with Timiskaming rocks, and along the Larder Lake Cadillac break, we have a panel of metamorphosed ultramafic rocks of the Pichet group. So what we have here is a cross-section of the deposits along the break. And what you can see is that there are several zones with mineralization. So ore shoots, Ogmito, Cinderella, like Gamble, Astoria. And then east of this, East Bay and Bouzan becomes poor in gold. So we have gold endowed and poorly gold endowed areas in that segment of the Larder Lake Cadillac. And it happens to separate when there's a slight change in the orientation of the fault, but also the thickness of the Pichet group in those rocks. So what we did is we looked at the oxygen isotope composition of quartz in samples at different places within the ore shoots, outside of the ore shoots, and in the less gold-entered sector of the Ogmito-Bouzan area. And what we can do here is we've been able to calculate both the composition of the water in equilibrium with quartz and tourmaline, and the temperature of equilibrium between the two minerals. So what you can see here is the distribution of sample values in relationship to the presence of the ore shoot. And what you can see is that we have lower delta 18O values in the eastern part of the fault zone. And when we go west where there are ore shoots, we have higher delta 18O values. But also we can see that they define temperature zones with higher and hotter fluid compositions where we have large ore shoot along the panel of the Lauder Lake-Cadillac break. Interestingly, if we look at the depth of the sample and the temperature of equilibrium, we can see a broad covariation with a much higher fluid at depth and lower temperature fluids higher. So this, we think, indicate the infiltration of the metamorphic high temperature fluid. Again, 400, we had 550 for the end member. And it's mixing and cooling along that system. And it provides a very high temperature gradient. So we probably have the deposit forming in the mixing zone. And we have the fossilized mixing front between the high temperature fluid and the resident low temperature fluid with temperature gradient of tens of degrees per kilometer, per 100 meter. So what the next step we did in Ogmito-Bouzan was to look at, can we repeat this using numerical modeling? So I'll just show you the results of the BEST simulation, where we used 3D modeling of coupled advection, diffusion, fluid reaction between rocks and the infiltrating fluid. And what we are able to do is to reproduce the upflow zone that are found in the areas where we've analyzed it. And what it shows is that there is a infiltration of the high delta 18O fluid, high temperature, and it's mixing with the resident fluid in the rock porosity. When we go into low gold endowment sector, we see much less fluid infiltration, and we basically reach a steady state in the area within about 10,000 years to 100,000 years. So the fluid flow appears to be something that happens quickly, but then not shuts down, but doesn't change anymore the composition afterwards. So the model that has been come up with by Guillaume Raymond was one where we have infiltration of the metamorphic fluid in zones of higher permeability, the ore shoots in the deposit, and fluids were infiltrating either from the sedimentary rock of the Témiscamingue or the volcanic rock from the Blake River group in the East Bay Bouzan area, explaining perhaps the change in mineral composition in tourmaline. It's less rich in calcium than in the sedimentary rocks. But it also shows that most likely the gold is carried by the metamorphic fluid. This is something that will come back again. Okay, so if we move now to a different scale, we did the same kind of studies at the scale of the Val-d'Or vein field. Here we have the region that we modeled for fluid flow using the same kind of 3D advective dispersive reaction equilibrium. And what you can see are the different units that were put into the model. So we have zones of high permeability in red that are higher, larger. That's the first order shear zones. And we have the other faults that are known in the vein field that are associated with gold. So we did this modeling and we used different boundary conditions. And the boundary conditions, for example, shown here are the cross-section. And you can see the complexity of the faults that we had reproduced to try to reproduce the fluid flow pattern in the vein field. And in this system, we had the infiltration of the metamorphic fluid with a delta 18O value of 9. And it was reacting with the volcanic rocks and granitic rocks of the Boulamac batholith in this area. And the faults at different width, intersecting features, connection with the bottom of the vein field, the block model, or the top. So the results we obtain to reproduce the isopleth pattern with high delta ETNO value in the south near the Lauder Lake Cadillac break are produced only when we have a boundary condition. So it's a first order control on fluid flow. The boundary condition that were used to reach that were produced when the whole area of the vein field was infiltrated by a metamorphic fluid. But this metamorphic fluid was allowed to drain out of the vein field only along the trace of the main structural break, the Cadillac-Lauder break. The rest being largely being impermeable in the modeling. So that indicates that the upper crustal fluids, which are in the rock porosity, were drawn into the different feature fractures and shear zones, and then they were allowed to escape the vein field while new fluids were continuously infiltrating into the zones where the deposits form. So that's the product of the fluid mixing and fluid barometric exchange that I mentioned earlier that explained this zonation within the area. So how does the mixing happen? This has been a question that has been discussed for some time, and I think that Steve Cox probably has come with one of the best proposals to explain this. So the formation of these veins has been related to the what's been called the fault valve model, where there's a cycle of pressure increase up to lithostatic or near lithostatic pressures, where at that point there is a failure along a plane that causing a seismic event and slip. When we have this event, we have the infiltration of the deep-seated metamorphic fluids produced at depth by continuous prograde metamorphism. This is a source of continuous new fluids going up into the area where the deposits will form. As this pressure builds up, the stress on the fault plane decreased by the fluid increased pressure. When that reached a point where the tensile strength is reached, it will break, slip, and then we will have a rapid decrease in fluid pressure. That decrease in fluid pressure will cause the flash vaporization, the immiscibility that is shown by the stable isotopes, but will also cause fluid movement along the plane of the fault field vein. So this will cause mixing between various fluids. When we have this movement along the shear plane, there will be damage, structural damage caused by the slip, and this structural damage will connect fluids that are in the rocks nearby to being drained by the higher permeability caused by the fracturing. So this will enable inflow in the wall rock and then outflow back into the shear vein, causing the mixing between the infiltrating high temperature metamorphic fluid and the resident upper crustal fluid. And what we know from earthquakes is that these will cycles with thousands of swarms of vein failure for each major earthquake happening along the shear zone. So my view of this is that we have an area where we form the orogenic gold veins, which is nearby the major crustal shear break, but which is outside of it in subsidiary structures that you can see here. In this area, we are close to the boundary between the seismogenic crust, where we have earthquake, and the seismic crust, where we don't have. In this seismic crust at depth, we have metamorphism, prograde metamorphism, that cause fluid formation by transformation of water-bearing minerals such as chloride into less water-bearing minerals like amphibole. This produces up to 48% water, for example, by this mineral transition. These fluids will be migrating by buoyancy towards the surface, but there is a difference between, or a region in the crust where we have hydrostatic fluid regime from the surface, so connectivity to the surface, and then we reach a point where we are in a lithostatic regime. It's been known for a long time that this is a strong gradient in permeability in that area that indicates some sort of cementation or different modes of deformation. So this maybe lithocap is what separates the lithostatic fluid regime at depth, which accumulates the fluids, which are released episodically by earthquake that let them drain out towards the surface. Okay, so if we look at this and now move from the vein scale to the regional scale, we've been studying the flow of the auriferous fluids along the Lauder Lake Keswick break. And what you can see here is the sampling density that we have both from literature and the Medalla-Earth project, from east of Val-d'Or to Kirkland Lake. And the samples provide us with a unique opportunity to look at what's happening along the length of that major crustal break. So like in the Val-d'Or camp, we find, and here it's divided by different segments from well, east to the end of the west, but basically they change color. And what we can see is that like elsewhere, we have this isotope equilibrium between, for example, quartz tourmaline, quartz chloride that enable to calculate the temperature for each mineral pair. If we use that, we can look at, is there a temperature change of a change in the temperature of equilibrium as we go from east to west? And if you look at the color code of the colors of the temperature, you will find that it is not any consistent variation in the temperature. So the temperature field is not changing east-west. We've seen in some places where it's relatively simple, it changed vertically, but otherwise it's not systematic. If we look at the composition of water in equilibrium with quartz, tourmaline, and mica, then we have a different picture. Here we have values that change from low to high delta 18O values, and we can see that there is a region around Val-d'Or where the delta 18O values of the vein field fluids are lower than to the west. So there's something changing at about Canadian Malartic, where we switch from a slightly lower fluid regime, not fluid regime, but fluid delta 18O values, to fluids with higher delta 18O values from up to about 9 to values up to about 15, all the way to Kirkland Lake. We see this in the mixing arrays. So this is the mixing arrays that we have in the along the Lauder Lake Keswick break. And what you can see is that the Val-d'Or and Allais segment, which are the eastern part of the Lauder Lake Keswick break, seems to have a different mixing array than towards the west. So what we find is that there are small differences in the metamorphic fluid sources along the length of the break, but they seems to be all converging without something we cannot distinguish in terms of the other upper crustal fluid component. If we look at the delta D values, we see only one mixing because there is the overprinted effect of devolatilization and mica formation that removes water from the fluid and modify the delta D values. If we move now to the global scale, I'd just like to remind you this, this book, at Springer, there's one chapter that documents the light stable isotope composition of orogenic gold deposits. And I'll just show you some of the salient feature that we find when we compare Val-d'Or and look at the regional and global scale characteristics of orogenic gold deposits. So first of all, if we look at the most studied mineral, and we look at the quartz oxygen isotope composition, and we divide by the age of the deposits. So what you can see here, and what's been known for years, is that if we look at the Precambrian deposits, they tend to have a lower delta 18O value compared to the Phanerozoic deposits, which tend to have higher delta 18O values. And this has been used to argue about cyclic change in the fluid composition in orogenic deposits, or a change in temperature between Archean and younger deposits, along with change in geothermal gradient purported for Earth. But if we do this study and we look at the dominant host of the gold deposit, what you can see is that those deposits which are hosted by igneous, plutonic, or volcanic rocks have a lower delta 18O values than those that are hosted by volcanosedimentary and sedimentary rocks. So this is really an effect of the country rock hosting the deposits rather than an age. And it works with the fact that those deposits that are Phanerozoic tend to be more often hosted in sedimentary rocks than in volcanic or plutonic rocks. If we look at this at a finer scale, here the scale of the craton, and this is for cratons for which we had more than 100 delta 18O values, what you can see is that each craton has a slightly different composition. So some are slightly lower in delta 18O, some are slightly higher in delta 18O. So each one has a different oxygen isotope composition. And if we move to the vein field, and here those vein fields that are within the superior, what we see is that each of them has a slightly different composition. Val-d'Or versus Timmins, for example. And this is something that's been known for some time, introduced by Rob Carrick, which he called provinciality. So there is a change in the metamorphic component that relates to the country rocks of each of the deposit. Again, if we look at worldwide, most deposits show isotope equilibrium between vein minerals. Sometimes they are not, but most are in vein equilibrium. And these temperatures of equilibrium are consistent with the equilibrium temperature of fluid inclusions. So there's a consistency in the data set regarding that. If we look at gold deposit worldwide, we see the same global mixture between high delta 18O value metamorphic fluids and lower temperature, low delta 18O value fluids, upper crustal fluids. But then there's also an added component of reaction with metasedimentary rocks, which cause a broader pattern in the database. And likewise, delta D values between the high temperature, low delta D value of the metamorphic fluid and the low temperature, high delta D value of the upper crustal fluid affected by boiling, immiscibility, and mica formation. So we have in orogenic gold deposits two common reservoirs. One is a high temperature, high delta 18O value that is most likely metamorphic in origin, but this fluid is always mixing with a upper crustal fluid, which the crustal rocks in their porosity contain water. It's not gas, right? The fractures, the pore between grains are hosting or contain water below the water table. This water remains there for a long time and reacts with the rocks. And that's the brine shields that are often found in deep mining settings. So you go in the superior craton and they make a drill hole and there will be water coming out. This water might be 10,000 millions of years old. It's been sitting in the rock for a long time and it changes composition similar to those of these brines. And when we go to the finer scale, and here I use two craton, the superior craton and the Yilgarn. And what you can see is that the Val-d'Or, volcanic hosted, is more like the Kalgoorlie and Coolgardie deposits in the Yilgarn craton, whereas the same difference exists again with the Timmins and Lauder Lake segment of the Lauder Lake shear zone. So we have variations in the proportion, most likely, in the magmatic and sedimentary rock in the different vein fields that are reflecting the material that is being metamorphosed at depth. And this is causing the provinciality between the different areas. But so far, we cannot distinguish variations in the upper crustal fluid. So we have one common composition, and perhaps this is because the long time reaction between the rocks and the water brings a rocky equilibrated composition that is not distinguishable. So in conclusion, I hope I've convinced you that there is isotope equilibrium between mineral pairs in orogenic gold deposit, and this enables us to calculate the temperature and a fluid composition. Using that, we can show that there is provinciality in the source of the metamorphic fluids. But this provinciality is the product of variation in the composition of the regional country rocks that undergo metamorphism at depth. So the same country rock package that is at the surface or hosting the deposit is being metamorphosed at depth. And remember that these deposits form close to the brittle ductile transition where we go from seismic to aseismic crust, and below that, that's where you're going to have the partial melting and the transition of minerals. The modeling shows that the shear zone formed transient breach at the hydrostatic lithostatic fluid regime transition. And that during these breaches, that's where fluid are able to drain out of the vein field. And this is enable more upwelling of metamorphic fluid that will be slowly replacing what's been moving out of the area of formation of mineralization. There's widespread mixing between metamorphic end members that are locally derived and upper crustal fluids, also locally derived. And this is a natural outcome of the fluid pressure cycling during earthquake swarm propagation. So when we have an earthquake that breach the lithostatic to hydrostatic transition zone, we have this series of readjustment within the crust, which will be small slip along all these small veins that will form the gold deposits. So the gold deposits are obviously in high flux zones and at the mixing front between the hot metamorphic fluids and the upwelling into the colder crust, where it mixes with the upper crustal fluids. And gold, most likely, like the quartz, comes from the metamorphic fluid, but then it becomes remobilized during younger events, so that the most of the visible gold that we see appears to be only remobilization of gold that was present into younger textural settings. Outstanding questions that we can ask ourselves now. Prograde metamorphic dehydration reactions, chloride out, is something that is common in metamorphic settings. It's not something that is limited to where we have gold deposits. So what's the difference? What makes metamorphic auriferous fluids migrate and form orogenic gold deposits? Golden fluids are extracted from volcanic and sedimentary rocks during prograde metamorphism below the vein field. The auriferous, that's what we know, the auriferous fluids infiltrate the brittle ductile crust during the propagation of dike swarms. And they precipitate gold by a variety of process, boiling, immiscibility, sulfidation, wall rock reaction, cooling, which makes it very difficult to find just one that is dominant anywhere. So what are the metamorphic conditions that enable the extraction of auriferous metamorphic fluids? This we don't know. If we compare this to the oil system, we don't know what kind of settings is favorable to the formation of an orogenic gold deposit. In the oil business, we know what kind of rocks, what kind of composition in terms of organic carbon can form oil. We know what kind of barrel rate it needs to go through the oil window, and then it has to stop so it doesn't go into the gas window. This is well understood. We don't understand that for the formation of orogenic gold-bearing fluids. And what are the tectonic environments, and can we really think we have to have similar things in Archean, the Proterozoic, and the Phanerozoic that will enable these optimal metamorphic conditions that will produce gold-bearing fluids and move them towards the surface to form gold deposits? And then, what's the timing of metamorphic fluid generation with respect to gold? That's been a topic that we don't know. We have little information on the exact age of gold mineralization. We have little information of peak metamorphic age in most cases. So I'll leave you with these questions. Thank you.